So today we're looking at quadratic equations. In the first part, we'll look at the fact that if there's complex solutions, then they always come as a conjugate pair. Then we will look at a special formula that we can, or a special result that we can come up with if the coefficients of the quadratic are real. We will then look at how we can use the quadratic formula to help us solve quadratic equations problems where the solutions might be complex. And then finally, we better look at what we mean by a complex square root and how we can find them. So if z is a solution to the quadratic equation that we have here, then that means that az squared plus bz plus c is equal to 0. If we then take the conjugate of both sides, so az squared plus bz plus c conjugate is equal to 0 conjugate. We've just taken the conjugate of both sides. We haven't changed anything, so the result's still true. Then we need to know a few things about the properties of conjugates, and we'll prove them in a later video. So at the moment, we'll just use them and accept them, but we will come back and we will prove them all. And the first thing we need to be able to do is that the conjugate of a sum is just the sum of the conjugates. So what that means is that left-hand side there, the az squared plus bz plus c conjugate, I can break that up to be az squared conjugate plus bz conjugate plus c conjugate, and we know that's equal to 0 conjugate. Okay. The second thing that we need to know is that a real number is just its own conjugate. So that c conjugate and 0 conjugate, they're just c and 0. So I can get rid of the conjugates there. The next thing that we need to know is a product. A conjugate of products is equal to the product of conjugates, just like addition. So that az squared conjugate is just a conjugate times z squared conjugate, and that bz conjugate is just b conjugate times z conjugate. And then again, we've said real numbers are just their own conjugates, so that a and b don't need a bar anymore. And then the final thing, z squared is just a product again, so I can break it up. So instead of writing z squared bar, I can write z bar squared. And then finally, we've got the result that we needed. Now, I can see that if I just replace in the formula z with z bar, I still get an answer of 0. So if z's a solution, z bar is also a solution. So we've proven the result that if there's complex solutions, then they come in a conjugate pair. Now this second part we're not going to prove, but we will use the result quite often. I say we're not going to prove, I'm going to prove, you're going to prove in an exercise in the future, but it's where we're looking at a quadratic equation where the coefficients are real numbers. So that a, b and c in the quadratic are real numbers, they're not complex. Then that's when this result holds. And it says if I have a solution to that to a quadratic equation, z equals alpha, then we already know that z bar equals alpha bar is also a solution. So that means that the quadratic can be factorized as the product of z minus alpha times the product of z minus alpha bar. That's the solution to, or that's the factorization of that quadratic. And then if we try to expand that out, then we're going to get z squared minus twice the real part of alpha z plus alpha alpha bar, and we know that's equal to 0. So that result's going to be rather useful, both in terms of starting from this point and factorizing, or if we have a factorization, then we know we can expand it out in this other form. That's going to be incredibly useful to us in the future. Alright, in this third part, we're going to look at how we can use the quadratic formula to help us solve certain problems where there's complex solutions. Recall that when we came up with the quadratic formula, the proof of it required us to complete the square. Now on the screen you should be seeing that process happening now, completing the square. But here we realize that delta, the discriminant, can actually be negative, but we'll be able to deal with that now, whereas we couldn't in previous times. So I can, if I can find a lambda where delta equals lambda squared, then I can continue to complete the square and come up with a nice simple pair of solutions in terms of this number lambda. And hopefully you can see that all on the screen now. So the hard part's finding this lambda. Now it's probably easiest by way of an example. So let's suppose that we have the quadratic equation z squared plus 2z plus 6 equals 0. Then delta equals 2 squared minus 4 times 1 times 6. which gives us that delta is negative 20. Okay, so there's a negative there. That would have been a problem in the past, but that just means that delta is equal to negative 1 times 20. So when I'm thinking of, well, delta is going to be lambda squared, what's this lambda idea? I can see I'm going to end up with an I there, because I squared is negative 1. Okay, and in fact, 20 is coming from 2 root 5 squared. So I can rewrite delta now as 2i root 5 all squared. And therefore I can plug that into the two solutions that I just found in terms of lambda, and I get my two solutions to the quadratic equation. So the hard part was finding lambda. Alright, now we come to the final part where we need to look at square roots of complex numbers. And that's because if we're just blindly working with the quadratic formula, we may find a point where we end up with a complex number under the square root. And we need to know, well, can we find the square root of a complex number? Does that even make sense? And the answer is going to be yes. And how do we do that? So let's establish how we do that. Let's suppose that complex number x plus iy is one of the square roots of a plus ib. Then that means that I can write x plus iy all squared is equal to a plus ib. Then expanding out that left hand side, I get x squared minus y squared plus 2i xy, and that's equal to a plus ib. So now I can compare real and imaginary parts, because these are both just the same complex number. So I can compare the real parts and the imaginary parts. So that means that x squared minus y squared must be equal to a, and 2xy must be equal to b, or x plus y is equal to half b. So now I've got two simultaneous equations that I can try and solve, and usually they're pretty straightforward, but we may have to come up with another little helpful hint to maximize our success on this. So let's look at a simple example where we can pretty much just, most of the time we can hopefully just use the factors of b to help us solve the problem. So let's consider finding the square roots of 7 plus 24i. Well, from what we've just said, x squared minus y squared must be 7, and xy must be a half of 24, which is 12. So let's consider the factors of 12 and show how we, just by inspection, we can solve this problem for x and y. Because the factors of 12, 1 and 12, for instance, well, 12 squared's 144, take away 1's 143, that's not 7, so that doesn't work. Then I can consider 2 and 6, 36 minus 4, 32, that's not 7. That only leaves 3 and 4 as my possibilities. But then realise that the negatives work as well. Negative 3 and negative 4 both work. And the 4 and the 3, x is 4, y is 3 for that x squared minus y squared to give us the 7. So the solutions are 4 plus 3i and minus 4 minus 3i. They're the two square roots. But we can come up with another little trick to help us out as well. We've got those two solutions, x squared minus y squared equals a, and xy equals a half of b. Well, what happens if I square both of those and then add them? Another way of simplifying that, x squared plus y squared must be equal to the square root of a squared plus b squared. So now we can consider, instead of considering x squared minus y squared equals a and xy equals a half b, we can consider x squared minus y squared is a, and x squared plus y squared is equal to the square root of a squared plus b squared. I know that seems more complicated, but look carefully at those two left-hand sides. If I add those two, then I'm just going to isolate out x and solve for it. And if I subtract them, I'm going to isolate out y and solve it. So it often ends up being a much quicker and more efficient way of solving the problem. So that's something worth memorizing, I guess, is how to find square roots nice and quickly this way. It does make the process really easy. The other thing you need to think about is we're going to get two answers for x and y, and that second equation, the xy equals a half b, we can still use that indirectly to determine are the x and y's going to have the same sign or the opposite sign, depending on how that xy equals a half b works. Because if we multiply x and y together and get positive, they must be the same sign. So if b's positive, they're the same sign. If b's negative, then they're opposite signs. And that's it for quadratic equations.